All right. So, good evening, everyone. So we are back fully to this second class. I just need a confirmation that whether everyone can hear me properly. I can't see you people, so I'm just a bit skeptical as to whether I'm audible or not, or it is clear. Yes. Okay. Thank you. Yes. Yes. Okay. So, yes, it'll be a continuation from last class. Okay. So, don't think what you know or what you will come to know. Okay. What matters is how much attention you pay, how much you grasp in the class, and how much you study well and then revise well. Okay. So today we'll take up the first and foremost topic in the spectroscopy, which is very important and which is one of the most basic techniques that is used in any of the analytical laboratories you go. So it also makes use of the electromagnetic radiations component for its working, and thereby we'll see how we can exploit this technique in order to obtain fruitful results, or those results which are actually useful for us to obtain certain experimental data which will prove that what our sample or what our experiment or what our analysis is. Moving forward, I just wanted to know that I will not be taking up this class on a monotonous mode and in a one-way mode. I will be expecting you people to participate. Yes, since you people don't have to speak, but keep your chat boxes open, and I need a pen and a book. So at least if you don't want to write the notes, it is your choice, but make sure we will have some practice sessions today, and you will have to do it, and I will be waiting for your answers. Unless I don't get answers, we will be not moving forward. So it will not be a session where you will just listen and then forget. No, we are not watching any sorts of cartoon movie here. You will have to uh, listen to the class, think, analyze, give an answer, and then we will proceed. Okay, so starting with the UV spectroscopy. Uh, the first thing, like in last class, I have mentioned that the energy that is there in the form of a photon or in any form is actually, when it comes to light, it is represented as a wave function. So you can actually directly precisely mention it as a sinusoidal wave function. And it is given by the most common equation E is equals to h nu, where nu is the frequency of the wave, and therefore nu is also equal to c by lambda, where c is the speed of light and lambda is the wavelength of the radiation that we are interested to study. H is the Planck's constant. Okay, so this is the same, might be a little bit of revision of what we have discussed in the last class. So we all know electromagnetic radiations, particularly the UV visible and IR regions, are majorly responsible for outer electronic transitions and vibrational or rotational transitions. So this is how you have to remember every time, since I keep on repeating this. Okay, since I keep on repeating this slide, it is just because to make sure that don't get lost. This table will help you. Uh, 1 second. Yes. Uh, to make sure that we go ahead without any problems and learn all these things, you have to keep looking at this table. I don't ask you to by heart. Maybe you will, if you by heart these wavelength values, then you will go through one another book and you will say this, sir, whatever you have taught is wrong. No, I want you to remember the left hand side, that is this EMR portion. Okay, this EMR portion. Okay, what happens when we go down the table. Okay, energy decreases, so the wavelength will obviously increase. And what kind of a transitions do these wavelengths or these radiations induce in a molecule or a sample that we are interested in? Okay, so to proceed further, directly we will be going into the UV spectroscopy, where we will have to see few rules, regulations, which actually guide the UV spectroscopy. So mostly starting with UV, we all know that you might have referred in your normal regular classes regarding the transitions that might have take place. So you must have gone through few of the transitions like sigma to sigma star, okay, pi to pi star transition. So what happens actually when a radiation falls on your sample? Okay, uh, so can you people hear me? I mean, I just got a message from people that I'm not unable to hear you.
Yes, sir.
Okay, okay, that's fine. All right. Great. So when radiation falls on a sample, what happens is we know that uh, the various electrons or different shells can be disturbed, okay, with the energy of the radiation. Okay, suppose your energy is having more, your radiation is having more energy, it will penetrate inside and it will disturb the inner electrons. Suppose you do not have, the radiation doesn't have proper energy, it will just go to the outer shell. In order to do this, we all know that what is sigma, and there is a sigma star. What does this star represent? Uh, do not take this star to be an excited state. No, it is not an excited state. Excited state is a different energy level. But here, sigma to sigma star or pi to pi star, this star doesn't indicate a uh, I mean energy level. It is something that is hypothetically shown, or it is derived, that if a sigma electron, okay, if a sigma electron is disturbed, it might take any of the transitions. That means it can go anywhere, not necessarily to sigma star level. But the star doesn't represent any energy level. Do not get confused to that. Okay. Now, how do you know that some transitions might occur or some transitions might not occur? Remember, there are different theories that have been postulated for this, but altogether what you have to remember is there are only some rules, or there is basically one or two simple rules which guide you to choose that which kind of transition will take place and which transition will not take place. So among them, the first thing about choosing a transition is a selection rules. So the selection rule tells us that the electronic transition between similar spin quantum number is always allowed and other transitions are forbidden. You have to remember this, that what kind of a transition is allowed. Always remember that any transition between similar spin quantum number. I hope you remember what is a spin quantum number from our intermediate. Okay, these quantum numbers are nothing but these are experimental values. Okay, so don't go into deep. You don't have to now uh, remember how a spin quantum number is determined. Okay, so don't worry about that. uh, but remember, only if the spin quantum number is similar, only the transition will be allowed, but all other transitions are forbidden. Now, what are the transitions actually? Okay, the transitions are, we know, sigma to sigma star, sigma to pi to sigma star, pi to pi star, n to sigma, n to pi star, and n to sigma star. Now you will have to remember what are the transitions that will take place and what are the transitions which will not take place. So we all know that sigma to sigma star will take place. Before we proceed what will take place, let us just see not or what will be restricted. These two kind of transitions. Okay, 1 second. Okay, this transition, okay, is not allowed, or it is completely forbidden. This is not allowed. So sigma to pi star will never take place, nor pi to sigma star will take place, because these two are in different quantum numbers. Sigma state and pi state are two different quantum numbers of a spin state. So it will never happen. Now, this n to sigma and n to pi star, we know that these will be taking. So these are something which will be termed as symmetrically forbidden. Sorry for my handwriting. It is symmetrically, TRICL, symmetrically forbidden. So the forbidden spelling is here. Okay. So it is symmetrically forbidden. What does symmetrically forbidden means? It is allowed only sometimes, depending on the nature of your molecule, and okay, depending of your nature of your molecule, and depending on the radiation that you're studying and what state the molecule is. Okay, it these kind of transitions should take place. And thus now you can see the most common transitions are sigma to sigma star. So what kind of transitions, which compounds will exhibit sigma to sigma star transitions? We all know all the saturated compounds, or commonly we call them as alkanes. Alkanes, and also cycloalkanes. Okay, these compounds will exhibit sigma to sigma star transitions. The next question which will come for you is, if a sigma to sigma star transition is happening, in which EMR region will this radiation will fall? It will fall under vacuum UV region.